Okay. Yeah, thanks. I'm going to do this in English because we're also recording this, so I want to make it available to also non-German speaking audience. Yeah, so as JP said, I'm Lukas. I'm from Codeplay. I'm going to talk a bit about SYCL, GPUs, LLVM, and MLIR today. Not going to read out the whole title for you. So next 30 to 40 minutes, I'll try to cover basically three questions. The first one is, what is SYCL and how you can use it to program your GPU? The second one is how we compile SYCL with LLVM. And the last question is how we seek to improve SYCL compilation with MLIR. And because MLIR is not yet like a household thing, I'm also going to talk a bit about what MLIR is anyway. If at any point you have a question, feel free to interrupt me. Just speak up, raise your hand, whatever. So happy to take questions in the talk, and I'm also going to leave some time for questions at the end of the talk. Before we dive into the technical stuff, maybe a few words about Codeplay, because it's also not a household name yet. So Codeplay is a little more than 20 years old, 21 years now. We've grown to about 100 people. And last year, around this time of the year, we were acquired by Intel, and we are now a wholly owned subsidiary of Intel. And our main mission is to make HPC and AI open and open source. So we are governing something called One API, which is an initiative initially started by Intel, but now governed by Codeplay, which is all about developing an open ecosystem for heterogeneous computing. On this last bit, we're also doing a lot of cutting edge research. For example, I do, and what I'm going to talk towards the end is more on the cutting edge research side of things. So yeah, this is Codeplay in one slide, basically. Okay, so with that, going to talk a bit about what is SYCL, by the way. So I think we can agree on that these days it's established that we will need GPUs and we need GPU compute to fulfill some of the computational tasks that we have, and we need to program these GPUs in some way. And one of these answers to that is SYCL. SYCL is an open standard. It's governed by the Kronos group. So every member of the Kronos group, everyone can become member of the Kronos group, and every Kronos group member can get involved in the SYCL spec development. The SYCL specification specifically is also open source on GitHub, so you can also contribute to the SYCL specification through pull requests and issues on GitHub. And the most important thing about SYCL is this: we provide a single source programming model. So in contrast to other programming models that you might know, for example, OpenCL, you don't have to split between host and device code anymore. You can have that in the same file. And the other big feature of SYCL is it's very strongly based on C++ and especially also modern C++. So we use a lot of the features from modern C++ to do heterogeneous computing. This is a little bit an overview of the ecosystem. There's more implementations out there that are more on an experimental side, on research side, but there's two main production-ready ones. The first one is DPC++. I'm going to talk a bit more about that during the talk because it's mainly implemented by Intel and Codeplay. And with DPC++, you can target basically GPUs from all the three big vendors, so Intel, AMD, and NVIDIA. Anything that can run OpenCL can also run DPC++. So if you have a OpenCL compatible accelerator, you're able to run SYCL on top of it. And the other big implementation is actually coming out of a university, just like 40, 50 kilometers south of here, out of the University of Heidelberg. It's called HipSYCL for historic reasons. I think they're currently in the process of changing that name. And with those, you can also target any CPU through OpenMP. You can target AMD GPUs, NVIDIA GPUs, and also Intel GPUs. So you have two really big and production-ready implementations that you can run on different hardware with. And that's also one of the big strengths of SYCL, to be portable across different devices. So yeah, what is SYCL in code? There's a few common patterns to SYCL that we try to follow in the development. And the idea is to use C++ and use things like lambdas to make some things more easy to express, to require less boilerplate code. For example, to do platform and device selection, or to do buffer creation and data movement, to move data from your host to your GPU and back, to compile your kernel function in the first place, and also all the dependency management, because a typical application will not just be one GPU kernel, it will be multiple GPU kernels, and you need to make sure that they run in the right order, because otherwise you're screwed. We always have this very nice picture here, so if any one of you has written an OpenCL implementation, you probably remember you have that bit in OpenCL C, so C, of kernel in a separate file somewhere, and you have this vast amount of C code or C++ code to do the host stuff for your application. In contrast, you can write the same Hello World application in SYCL with that bit. But talk is cheap, so let's maybe look into an actual Hello World application in SYCL. So what we're going to do is we're going to add 2 vectors, so simple parallel thing you can do. Yeah, we have standard C++ main function, we have standard C++ vectors for our data, and the first SYCL specific thing we do is we have this queue here. And a queue is basically just something that you can submit work to, and that work then gets executed on some device. With the default constructor here, you would get the default device in your system, but you can also specify you want a GPU, you want a CPU, whatever kind of device you have in your system. Next thing we're going to do is we're going to create some memory buffers. Those simply wrap the standard vector from up here in a buffer. That itself is not going to do much. It's just a way of saying to the SYCL runtime, okay, this is some data that I want to use later on some device, for example. Okay, so then we're going to submit some work to our queue. And the first thing we need to do, we need to get some access to data on the device. So we create 3 accessors. The first 2 for our inputs are read-only, as you can see here. And the last one is write-only, and we don't need to initialize the data on the device because we will write all of the data. This is going to do 2 things. One hand, it's going to inform the SYCL runtime that we need this data for this kernel on the device. So this will trigger the data movement from your host to your GPU, for example. And the other thing it's going to do is going to set up dependencies. So because of that, we know we have dependencies on these buffers. If we were to submit another kernel that requires the same buffers, the SYCL runtime through the accessors knows that there's 2 kernels requiring the same buffers, and will make sure they get executed in a way that there's no data race, for example. And now the last bit, that's the bit that actually gets executed on the device. So this is your whole kernel function. What you used to put in a separate OpenCL C file for OpenCL is this C++ lambda here. The only parameter you take is an ID. That is your position in the grid where you execute. And what we're going to do is we're going to take an element of A, we're going to take an element of B, add it together and store it. That's all. Yes. Yes. You can have 1 dimension, 2 dimensions, 3 dimensions. And here we're saying we only want to execute in 1 dimension. You could also have a 2-dimensional, then you can do, for example, tiled accesses and stuff like that. Yes. This is essentially this 3 opening angle brackets in CUDA is the equivalent is this here. Sorry? Yeah. Yeah, and that's it. That's all you need to do for a SYCL application. You can put that, okay, you need data include, I admit that, but you can put that in a file, you can compile it with a SYCL compatible compiler, you can run it and it will execute on your default device, which could be your GPU, for example. So it is as simple as I tried to say. Yeah, sure. Yes. Yes, an accessor is a pointer plus the range it can access, and it's mandatory to use capture by value here, because if you captured by reference, that reference would mean nothing in device memory, because it would be pointing something in host memory, and if you don't have shared virtual memory, you can't access that reference. So capture by value is mandatory here. Yes. Yeah. No, you wouldn't be, but for USM, we have you can allocate buffers directly in shared memory, pass in the pointer, and use that pointer inside there. So you can also do that. That was added in SYCL 2020 support for unified shared memory. Okay, yeah. No. Yes, you can put whatever name you want here. It just needs to be forward declarable, so you need to put it up here. But most SYCL implementations also allow you to put it just here. You could just put class add here, omit that up here, and you're fine. It's just a name for your kernel, an identifier. Some SYCL implementations even allow to not put any, so to do an anonymous lambda here, and they will just make up a name for you. Make sure you get a unique name then. Any other questions? Okay. So I see I got a lot of people interested in SYCL, so you all want to learn more about it. Unfortunately, I won't be able to cover like a whole SYCL tutorial today, but there's this cool website here, it's backed by Kronos, SYCL.tech. Essentially from this slide, if you remember anything, remember SYCL.tech, because all the other resources that are on here are linked on that web page. There's also overview of projects that use SYCL, for example. There's a book, a free ebook actually, that you can use to learn about SYCL. It's called Data Parallel C++, and was written by a few people in Intel, so that you can use it uses parallel programming in the beginning and then talks a bit more about SYCL. And if you want to try out compilation for SYCL, you can also use Compiler Explorer using this somewhat lengthy link. So remember SYCL.tech, and the link should be there. Okay. Done. We can talk about the second part. So we're the LLVM social, so let's talk about how we can use LLVM to compile SYCL. So something to remember is SYCL is a single source programming model. You can have your device kernel in the same file as you have your host code. And so the compiler needs to compile for the host and for one or multiple devices, depending on how many different devices you want to compile for and how different the architecture is. And the typical approach, it's not mandatory in SYCL. You can take different approaches, but a typical approach that you see in SYCL compilers these days is something called single source multiple passes. So you take the same source file and run it through the compiler multiple times, filtering out the stuff that you're interested in. Sounds complicated, but as a user, it's not something you need to worry about because it's all orchestrated by the compiler driver. So usually you just put in one flag and the multiple passes will happen for you in the background if you even need to know about that. I've been mentioning DPC++ a few times now. So it's Intel's open source SYCL implementation, and it's essentially an extension of Clang and LLVM. So fork of the LLVM project, adding some SYCL stuff in there, adding a SYCL runtime, and that's about it. Okay, so how does the compile flow work? So we have our source file, some C++ file, and we have our compiler driver, simply Clang. And then we start with the device compilation. So we have a SYCL device front end. The device front end will take care to make sure that we get the right entry point for our kernel because they are specific to the architecture or the ABI of that architecture. And it will also filter out the host code because we don't need to compile the host code for the device. That compilation will then produce some device binary. On CUDA, that would be PTX or a QBin. On Intel architectures, we typically use SPIR-V, which is an LLVMIR-like format. So the final compilation to device binary happens through the driver at runtime. So you still have you can use the same SPIR-V file for an Intel CPU and for an Intel GPU. So you still have some leeway there. Goes through the offload wrapper, similar to what JP showed in his talk about for the OpenMP offload wrapper, and you get a wrapper object, which is essentially a C++ object file. The second output from our SYCL front end is something called kernel layout information, so some information about the parameters of your kernel, some other stuff that you need on the host side. On the host side, we also have a C++ host compiler. If you use DPC++, the default will be Clang, but most SYCL compilers also support you to plug your own host compiler in here, because the layout information coming here is essentially just a header file. You can include it in your source file, and you can run that thing through GCC, for example, if you wanted to. Yeah, it's essentially saying, okay, it's that and that argument of that and that type, and that's the way you're. The thing in SYCL is, because you have these lambdas, for example, what you have is a kernel function object, and the layout information also says, okay, that parameter is stored at that offset in that kernel function object. So the runtime can pull the parameter value from the object and then pass it to the device driver runtime. Yeah, and then you compile, you get a host object, again, just an object file, and then you use your standard linker and you get your application, or sometimes also called a fat binary because it includes the host and the device code for that. Yeah, and that's all how you can use Clang and LLVM to compile SYCL, so not that complicated. I mean, there's a lot of complications in the details, of course, but unfortunately, I also won't be able to cover all of these today. So the good thing is DPC++ is open source, so you can simply go to github.com until LLVM and just look at the implementation if you want to. There's also some really nice documentation about the compiler and runtime design on this somewhat lengthy URL down here. And one thing I was already asked about before the talk, what about upstreaming? So there's actually an ongoing effort to bring this SYCL implementation based on Clang and LLVM into upstream LLVM. So the vision is that sometime from now, your Clang that you get from LLVM.org will be able to compile SYCL programs and run them on different devices. There's basically a call happening to discuss technical details, and then there's going to be an upstreaming effort to bring that all into upstream LLVM. Yes. Okay. Before we can, any questions at this point? Yes, sorry. I think it's Mondays at afternoon. I can find out. It's in the LLVM calendar. You should be able to see it there. Yeah, so ICPX, the one that you get from Intel these days, can also compile SYCL. Clang, obviously, HipSYCL also uses a version of Clang for that. Unfortunately, right now there's no SYCL implementation in GCC, although nothing would prevent them to implement one. So it's nothing that anybody stops them from doing, basically. Any other questions? Okay. So yeah, before I can talk about the third part, I wanted to give an introduction about MLIR, because some people maybe heard about it, some people only heard the name maybe, and sometimes it's the easiest way to explain something is to explain what it's not. I've quite a few times heard it's a machine learning oriented IR, which is not true. It's also not a machine learning framework. So MLIR is essentially compiler infrastructure. It's not something you can use to replace PyTorch or TensorFlow in any way. Even though the ML in MLIR might be a bit misleading here. And it's also not LLVM on steroids. So it's not just some additions to LLVM-IR, there's some fundamentally different design involved in MLIR. So the motivation, and I honestly just took that from Chris Latner, who initially concepted MLIR with a few other people at Google, came from this picture essentially. So we have most LLVM-IR or LLVM project has a lot of front ends, and a lot of front ends use LLVM-IR in some capacity because LLVM-IR is cool because you can target a lot of different devices. You have this one target independent IR, and you have backends for x86, for ARM, for Spark, for Tiger processors in your PlayStation, and so on and so forth. So that part works well. What doesn't work as well is that front end part here. It's like an earthquake. So we have a lot of languages that use LLVM for their compiler, but none of them go from their abstract syntax tree directly to LLVMIR. So Clang has SYCL, although that is not the default path for Clang. But for example, Swift has this Swift intermediate level representation. Rust has something in between. I think Rust even has 2 in between. We have Julia, which also has something in between. And I mean, talking about machine learning frameworks, there you have even higher level because you come from like a graph, which is just a graph of convolution operations and pointwise operations, and you go through a few steps before you go to LLVMIR. And why is that? The problem is we come from our source code, we go to our AST, and that is a small step. You basically just omit all the things that are there for syntax, but not for semantics. So that's a small step. And going from LLVMIR to assembly is also a small step with machine IR in between. But essentially, LLVMIR is a 3-address code. And if LLVM doesn't have a representation of loops, how to represent loop in LLVMIR is you have blocks and you have jumps between them, but you don't have loops anymore. And the problem is, in that step, we lose a lot of information. All your structure from your language is gone. Your loops are gone. You lose a lot of information that would actually be quite useful for a compiler to do some fancy optimizations, for example. So that's why many languages introduced one or multiple boxes in here to make sure they make smaller steps and can use that intermediate steps to do reasoning at a higher level of abstraction. And that's exactly where MLIR can come into play. It's not the only way you can use MLIR, but you can use it that way. You have something called dialects, and a dialect is essentially just a unit of some domain-specific abstraction. For example, there's a dialect to represent loops or control flow in general. There's a dialect to represent vector arithmetic, because all that isn't there in LLVM, or if it's there, it's on a quite low level. And by combining multiple dialects and going from one dialect to the other in small steps, we can achieve that we have this gradual lowering in smaller steps, and every transformation can work at the right abstraction level. So if I'm interested to transform some loops, I can live here where I have a loop dialect or a control flow dialect and can use that information to transform my loops, for example. So the whole idea behind MLIR is to create an infrastructure that allows people to design those dialects and use them to represent some high-level information that you need for your compiler. As I said, that's just one way to use MLIR. That's another way. All of these boxes here are MLIR dialects. So you come from TensorFlow, you come from PyTorch, you come from ONNX, which is essentially also a machine learning format. You go to something called TCP, tensor compute primitives. So essentially a few primitives operating on tensors as a data type, or something called stable HLO, which is similar. And then you go further down. You have the tensor operation set architecture. That's something defined by ARM, I think. You have the linear algebra dialect, which represents typical BLAS operations, for example. You have the affine or SCF. SCF is structured control flow, so it's exactly what I talked about, a dialect to represent control flow like loops. Or you can go directly to some library like QDNN or Q+. So this is another way of using MLIR. So, and a dialect in MLIR is essentially just this. You have a bunch of operations that you can define. You have a bunch of types, for example, a tensor type if you need that. And you have some attributes, which just compile time values. And that's your dialect. MLIR makes it easy to define those dialects and to use them and to combine them. So a compilation flow will not just use one dialect and then go to LLVM-IR. It will typically use multiple dialects and even multiple dialects at the same time. So what you can do is you can use a loop from the SCF dialect, put some memory accesses in there using the memref dialect, which is a dialect mainly concerned about accessing memory in a way, and then have some arithmetic operations from the arithmetic dialect. And you combine these three dialects to express a loop doing something arithmetic on a bunch of memory. And LLVM-IR can also be represented as a dialect. There's actually an LLVM dialect, so many compilation flows today will use some of these higher level dialects, do some optimizations on that high level of abstraction, lower to LLVM dialect, and then from LLVM dialect you can easily go to LLVM-IR because it's more or less a one-to-one mapping, and then you can use the full power of LLVM to compile your executable at the end of the day. You can still have all the LLVM optimizations running on your LLVM-IR, and you can still target all the backends that LLVM already has. So that's why MLIR is also built on like a very solid foundation when it comes to backends. A quick overview of how an operation looks like, because we're going to see some examples, and I wanted you to be familiar with the syntax. So this would be a store operation from the affine dialect in that case. We have some attributes, as I said, these are just compile time constant values. In that example, we know that we will always index the zero index of that pointer, for example. We have a type. In this case, we have a memref. It's a dynamically shaped memref, so we don't know how many elements will be there, but we know there will be some elements, and the type of the elements will be float 32, so basically an array of floats. A quick example, so this is C++ or maybe even C, I'm not sure about that. And you can compile that to MLIR, and you get something like this. So you have a function up here. You have the name test. This is mangling, C++ mangling, so nothing specific to MLIR. We have this alloc A, so this is the equivalent of allocating that array here on the stack. And because it's allocated with a constant size, we now also have this shape information. So now we know it's 16 integers that we have here. And then from the affine dialect, we have a for loop where the argument will iterate from 0 to 16. That's exclusive to 16. An index cast is basically just casting an int to something that you can use to index memory. And then we have a store where we store the value here into that alloc A. And this is the return. We cast again, we load something, and we return it. And the difference to LLVM-IR in that case is we still have a loop, for example. In LLVM-IR, that would be at least 3 basic blocks, and then some branches, some conditional branches to represent that loop here. Okay. So much on the background about MLIR. I think a full MLIR tutorial takes like an hour and a half, so I won't be able to do that today too. Only URL you will need to remember for MLIR is mlir.llvm.org. You have tutorials, recorded tutorials, and also some written tutorials if you want to get started on MLIR. You have documentation for all the upstream dialects, for example. You can have a look at MLIR has this nice weekly open design meeting where they discuss things around MLIR. All the videos from that are recorded and put also on this website, so we have really a lot of video material. Also, there's the keynote where Chris Ladner initially announced MLIR 5 years back now. So all that is available on the website here. Yeah, this is the weekly public meeting I was talking about. So yeah. So now we have all the pieces in place, and now we can think about how are we going to use MLIR to improve compilation for SYCL. And we can go back to our nice compilation flow picture from the beginning and realize one thing. There's a flow of information from here to here. What we don't have is an information flow from here to here. So in the host, we get some information about the layout and the device, but during device compilation, we never have any information about what's the context that this kernel is called from. Are some of these arguments maybe constant? And all of this information is missing because we don't have this arrow here with the current compilation flow. And that's why we're working on a project that we call SYCL MLIR. And the very broad aim, is to have better optimizations for SYCL. Better optimizations for the device code. So because MLIR gives us a powerful tool to represent some of the things in the device code, we can better optimize them because we can better understand them, and we don't need to basically try to retrieve as much semantics from LLVM than before, because we now have a higher level representation. I'm going to show you an example of that in a minute. And the other thing we want to do, we want to optimize across the border between host and device. So we know something about the host, we know something about the device, and we want to use that to optimize across that border. And for that purpose, LLVM is just not enough for us. It's too low level, as I said. We don't have loops, for example, for our optimizations. And currently in LLVM there's no way to represent host and device code in the same file, in the same module, because you have different target triples, and an LLVM module can only contain one target triple, so you cannot have both in the same file, for example. And the idea is that MLIR is just better suited for that. We can use the higher level abstractions, as I said, and MLIR has this built-in concept of nesting. You can nest operations inside of operations, you can nest modules inside of modules, and that allows us to nest the device code inside the host module and optimize both at the same time. So the very broad objective that we set out to do, or we're still doing, is to build an MLIR-based SYCL compiler. How do we do that? First thing, of course, is we define an MLIR dialect for SYCL. And the idea is to capture some of the semantics of SYCL and some key abstractions. That would be data access, the accessors and the buffers that I've shown you in the beginning in the SYCL part. Some of the parallel semantics, because you define the function that each work item executes, but of course that function is executed by a lot of work items at the same time on your GPU. So we need to capture some of that parallel semantics in there. And then we're going to represent the host and device code in the same MLIR module to do analysis. Right now, we'll mainly do analysis of the host code to get some context information that we can use for optimization of the device side. Again, I want to show you an example, because sometimes an example is just more powerful than me talking for half an hour. We want to do a simple optimization on that for loop here. So we have this for loop. And in each iteration, we add something to our accumulator, but we store that to memory every time around. And that's not efficient, especially if that is, for example, in global memory on your GPU. So what we do instead is we want to have a local variable. We initialize that with the value. In the loop, we always perform that addition to that local element. And when we're done, we can write back to our global memory. Okay, this is just an excerpt of the LLVM for that. And essentially, there's calls here, there's some address-based casts here, but you cannot really, if you look at it for long enough, you'll notice that this is a mangled name for accessing this ID here, and this is the mangled name to call the subscript operator on this accessor here, for example, but it takes forever to see that and to analyze that. So can we have a better representation of that? It turns out we can. So we have a SYCL constructor for our ID, so for this bit here. We have an operation, an MLIR operation for the subscript operation on our accessor. So we have the accessor and we have the ID that we use to access it. And we have the load, we have the add, and we have the store. And with that, much higher level representation and also domain SYCL specific representation, it's much easier to do optimizations than it was with that LVMIR full of calls with mangled C++ names and pointers and whatnot. And this is exactly what we want to leverage from MLIR, this kind of higher level representation to do optimizations. There's one big challenge for us right now, and that is front end. There's no default front end like Clang that you can simply use to go from C++ to MLIR. That's the challenge right now. We have two different approaches right now. For device code, we use a project called Polygeist. It's a scientific project coming out of MIT, if I'm not mistaken. And they can do a lot with C++ code to MLIR. So they can consume, essentially they're living behind the Clang AST and then can use the Clang AST and compile that to MLIR, and they can cover a lot of C++. And SYCL device code has some restrictions. For example, there's no virtual functions in SYCL device code. There is no dynamic memory allocation in SYCL device code because that doesn't map well to GPUs. So Polygeist can cover all that. But it does not support enough C++ to do that for the host code, because SYCL host code is C++ code. No restrictions. There's exceptions. There's dynamic memory allocations. There's virtual functions. There's all the nastiness of C++ that you can imagine. And so for that, unfortunately, right now we need to use a different approach, which is we compile to LLVMIR. We use a tool that comes with MLIR that can raise from LLVMIR to the LLVM dialect in MLIR. And then we can do some further raising to get to something that I just showed you, some SYCL specific types. But you're all shaking your heads, and rightfully so, because that's not what we want to do. Because it loses all the advantages. We make that big jump and then try to go up the stairs again. It's just, we want to do small steps. And that's exactly the challenge right now for us. We have this big step and we don't know how to do a small step. There's multiple ongoing projects for C++ frontend for MLIR. One of the promising one is ClangIR. Was started about a year ago from two engineers in Meta or Facebook, however you want to call it. It's now an LLVM incubator project. It's also open source, clangir.org. Their repository also lives under the LLVM Foundation. So they set off to do mainly static analysis for C++, that they're also interested in lowering from their C++ MLIR dialect to more low-level dialects. So that's one interesting approach. The other is called VAST. That's a DARPA-founded project, also about safety and security in C++ code. And they also consume the Clang AST and then use MLIR to go step by step in C++ abstraction levels. But right now, there's no definitive solution. We hope that one of these projects will eventually yield a nice C++ front end, but it's not yet there. So for the time being, we will have to stick to that and then maybe transition to something down here. That's a challenge actually on that slide. ClangIR, so they have, I mean, the project is called ClangIR, but they also have something called ClangIR, which is essentially an MLIR dialect that can cover a lot of C++. There's still some corner cases in C++ they're still working on, but they can cover that. And for example, they implemented a static lifetime checker based on that Herb Sutter paper for C++, and they used that inside Meta for production code to do some fancy static analysis checks. So it can cover a lot of C++. The lowering from that ClangIR to other MLIR dialects hasn't been their first priority, but there's right now an ongoing Google Summer of Code project tackling exactly that. And that student has made great progress in the last 4 or 6 weeks since the project started. So yeah, I think by the end of, or by fall, ClangIR should be able to compile much more of C++ to lower level MLIR dialects. VAST They're also working on end-to-end compilation, but for them it's mainly about verifying that their front end does sensible things. It's not so much about performance optimizations. So for the raising, how much work do we pour in there? As much as needed, as little as possible, essentially. So we try to raise, and we're successful in raising. We find out a few nice things about our accessors. We find out a few nice things about the calling context. We use that information and basically go on an as needed basis here. Polygeist, unfortunately, the project hasn't been super active. We've done a lot of maintenance for our fork of it to make sure that we can run it, but also going to be an interesting thing between Polygeist and ClangR, for example, in the end of the day. Okay. Again, I won't be able to cover all of the project, unfortunately. We had a LLVM Lightning talk about this project, and we had a poster there. And the development of that project happens in DPC++, essentially on a branch. So you can simply go to the URL for the open source DPC++ and find the right branch and then basically see our development happening there. Yes. And with that, I'm going to put on this nice notices and disclaimer slide and give you some time to think about questions, because that's the end of my talk. Thank you very much. So 5 minutes to pizza questions. Yeah. Yeah, sure. So, can you go back? Output, like I don't see the loop construct. Yeah, that's just an excerpt too. So the loop would be around that. So that the load would, for example, be based on the loop index then. But it's not shown in the picture, the loop here. It's just the SYCL specific part that I'm showing here. Yes.
SYCL dialect, and so is there some kind of core MLIR? Your compiler must be at least able to load those MLIR instructions before you can call yourself a fully functional MLIR compiler, because you design a SYCL dialect and it's a dialect, and probably not produce master dialect instructions.
Yes. So there is a set of upstream dialects that have proven useful to different compilation flows and can be reused in different settings. That would be one potential target for a C++ front end. Another potential target would be the LLVM dialect in MLIR. You lose a lot of the goodness, but then it's essentially about creating, for example, a plugin infrastructure where I can say, okay, I'm interested in anything that is in a SYCL namespace in C++, and I want to run that through my plugin, and I want to emit my own operations for that and not rely on your LLVM. If you have like a C++ front end that can lower all of C++ to LLVM dialect, adding these plugins or adding things that intercept that at some point, use some higher level dialect and then go further down, that's not the easy part, but it would be able to build on an existing infrastructure. Because for most of the host code, I don't care about the host code. I care about the bit where SYCL kernels are launched, but I don't care about the standard vector that I showed you in the beginning, how it's implemented in detail. That's something the LLVM dialect is absolutely sufficient for. The involvement, especially of the upstream dialects has definitely slowed down. I started using MLIR for my PhD project back in 2019, and if you did a pull down every 4 weeks, you spend a full day just updating your API calls and updating something because they changed some dialect. That has definitely slowed down. Back then the project was like a year and a half old. Now you have a 5-year-old project. You have multiple downstream projects relying on it. So the governance for upstream dialects, the governance for API changes has definitely improved in a sense that they will deprecate things first, announce when they make changes. So the governance model has definitely improved there. Yes.
I know SYCL is all C++. Looking at that and knowing that there's a Fortran dialect in MLIR, having this like nesting scheme, I mean, you can use like C bindings in Fortran. You can then, in theory, call into C++ from the C bindings.
Okay.
Would you be able to use these things in like the MLIR graphics potentially at least? To know, oh, I have this, do concurrent loop here where I do a bunch of stuff. I know like memory access patterns or bounds at least, and I then call into a C interface, which kind of loses a couple of those informations. But in theory, looking at the like host to device information flow, combining all of that stuff in MLIR, you could potentially figure things out, right?
I mean, MLIR has a module, but MLIR module is just an operation, and every operation can have a region attached to it, and inside that region it can have other operations. So for example, there's a GPU module operation in MLIR that you can nest inside the regular module, for example, and nobody stops you from putting another operation which has other things nested inside of it into that module. So it's not as rigid as LLVM where you have one module and you have functions and you have basic blocks and you can put instructions in there. You have these basic blocks, regions, and operations, and they can nest essentially infinitely. But I mean, there's a technical limit to it at some point and a sensible limit to it. But there's a nice graphic on MLIR, LLVM.org, where they essentially show, that's the nesting structure. It's basically operation, region, block, operation, region, block, and you could continue that basically forever. I can see it. Okay, thank you very much.